Dr. S.P. Arsa from Mechanical and Engineering Department, IIT Roorkee. In the course of vibration control, now we are discussing about the principles of active vibration control. So, in last two lectures, we mainly discussed about the basics of vibration control, means how do we adopt the sensing feature and how we coupled the sensing and actuator part with the automatic control unit. And also you see we discussed about the various part of the materials aspect through which we can couple both the sensor and actuator right from the material itself. So, you know, like we discussed various parts like the SIP memory alloys, the electrorheological, the means electrorheological or magnetorheological fluid, the electrorestrictive fluids, or even you see here the piezoelectric materials. So, in the last lecture we mainly discussed about the formation of the piezoelectric part, that how the piezoelectric, you know, like these crystals which has you see the crystalline features can simply give the electrical output when the mechanical input is there, or vice versa when the mechanical output is there, how the electrical input can generate such kind of things. Means we can have a clear strain feature which can be you know, like sensed, or even we can have the electrical charge feature when the mechanical forces are there. So, we discussed, you know, like main right from the Curie brothers in 1880, that how they, you know, like featured out this part when, you know, like when they say that when any this crystalline material is being there in the stress field, then the voltages are being generated, or when they are under the electric field, then the strain feature is being there within those materials. So, based on their internal stiffness feature, the actuation forces are being generated, and based on you see these whatever the molecular motions, whatever you see, either we can say the silicon oxide or anything you see, the sensing features can be adopted using that. So, this piezoelectric material can be used directly as the sensor or the actuator according to the requirement. But one of the drawback of this piezoelectric material which was discussed, that when the static force is there, then certainly you see here we cannot feature out the sensing part from this material. And you see here we discussed in the last lecture about the man-made or the naturally occurred piezoelectric part in the materials. And we found that there are lots of drawbacks when we are really going in the actuator part when we are using the naturally occurred material. So, one of the best use in the sensor and actuator part from the piezoelectric material is the PZT patch or the PZT material, in which we have the lead, the zirconium and the titanium part, and they, you know, like coupled feature is giving an excellent property, they are exhibiting excellent property which is being required for sensing and actuating application for active vibration controlled part. But sometimes even you see here the lead which is not, you know, like the environmentally compatible feature, there is a clear demand that you see here the lead free kind of system should be adopted in these ceramics part. So, you see here the sodium or the potassium based these materials are now being evolved, but still you see lots of things are being, you know, like requiring to be done in this particular part, but still the PZT part is commercially used, and still it is being, you know, like in the use of in the application, various applications are there and we are using that. So, as far as the application part is concerned, now in this lecture we are going to discuss about the principles of active vibration control, and you see here in this particular piezoelectric material what the applications are there in that. So, when we are talking about this piezoelectric material applications, we know that first thing is coming, there are various applications, and the first is the high voltage and the power sources. So, under this category the direct piezoelectricity of substance like the quartz or many other can generate the potential difference of the thousands of volts even. So, we can say that even the high voltage part can also be adopted as per the applications, and the best known application is the electrically cigarette charger, the electrically cigarette lighter. where pressing the button is causing the spring loaded hammering action, and when this hammer is hitting the piezoelectric crystal, they are producing a sufficiently high voltage electric current abruptly at that point, and which flows all across the small spark gap, and because of this heating part, the gas is being ignited and we have the lightning feature. So, this is one of the basic principle in which you see here the high voltage electric current is being generated, and that is being flowing to generate, or to we can say ignite the gas by heating part. So, this piezoelectricity is directly coupled along with whatever you see like the elements are there, and that is being generating a high voltage part there itself. Or even we can say that a portable speakers which is used to light the gas grills or the stove working on the same way, and many types of these gas burners now is being built based on the piezo based ignition systems, and that is one of the unique feature of that. So, piezoelectric transformer is a type of 8 AC voltage multiplier. So, unlike a conventional transformer which uses magnetic coupling between the input and output, this piezoelectric transformer uses the acoustic coupling, and an input voltage which is being coupled across the short length of bar of piezoelectric material, like like the PZT which we discussed. Through that we can create an alternative stress in the bar by inversing the piezoelectric effect, and then we can like cause the whole bar to vibrate. So, this vibration frequency can be chosen to be resonant frequency of the block within you see right from the 100 kilohertz to 1 megahertz range even. So, this is what you see the huge vibration excitations can be there according to the input voltage there itself. So, a higher output voltage can be generated all across the another section of bar just using the piezoelectric effect, and this step up ratio which is of more than 1000:1 can be straightway demonstrated using this. And an extra feature of this transformer is that by operating it above the resonant frequency, it can be even made up to appear as an inductive load, which is useful in circuit that require a controlled soft shaft starting part. So, these devices can be used in DC AC inverters to drive the cold cathode fluorescent lamps. So, this is again you see one of the important specific use of this, and these piezo transformers are some of the most compact high voltage sources, and nowadays they have lots of good applications in these, because these like the transformers are straightway we can say that just a AC voltage multiplier. So, this is one of the important application of these piezoelectric part, the piezoelectric materials, just to generate the high voltage or the high level of power sources, right from the electric lighter to even we have seen that the generators or the transformers. Second, as we discussed from the vibration point of view, is the sensor, and the principle of operation of the piezoelectric sensor is simply that the physical dimension is transformed into the force and can act the two opposing phases of the sensing elements, and depending on the design of sensor, the different modes to load the piezoelectric element can be used. As we discussed, there were 3 different modes: the longitudinal, the transverse and the shear. And whenever we are just going with the sensing elements part especially, then the transverse feature or transverse mode gives a proper feature of this sensing element. So, detection of the pressure variation in form of the sound is the most common sensor applications, like we are using the piezoelectric microphones, in which the sound waves bend the piezoelectric material and creating the changing voltage. This is what the application is, because we know that the sound waves have a sufficient power, and through that we can simply deform deform, or we can provide the mechanical strain part. Through that, you see the voltage can be generated. And piezoelectric pickups for acoustic electric guitars have excellent applications towards that. So when we are talking about the piezo sensor, which is to be attached to the body of the instrument on this particular guitar part, is known as the contact microphone. And this piezoelectric sensor, especially which is being used for high frequency sound in ultrasonic transducers, for medical imaging or even for industrial, we can say this non-destructive testing NDT part, has a greater applications towards that. So when we are talking about the sensing techniques, the sensor can be act both as a sensor and actuator feature, often termed as the transducers, which is preferred when the device is acts in this dual capacity. But most piezo devices have this property of reversibility, whether we are using as a sensor or actuator in the reverse phenomena or not. So when we are talking about the ultrasonic transducers, which can be injected, which can inject, you see, the ultrasonic waves into body, receive the return wave and convert it in the electrical signals, just like the voltage part. So most of the medical ultrasound transducers are of piezoelectric based only, because it has a great applications when such actions are being required under the ultrasonic transducers. So in addition to these mentioned, the various sensor application can also be there, like the piezoelectric elements are just using in detection and generation of the sonar waves. The power monitoring in high power applications, like you see the medical treatment, or you see the sonochemistry or industrial processing features. These are the clear application of these piezoelectric sensors. The piezoelectric microbalances, which are just used as very sensitive chemical and biological sensors. And even the piezos are sometimes used as the strain gauges, where a clear, like we can say, the deformation measurement can be there in that, even the micron level. So these transducers, the piezoelectric transducers, are used in electronic drum pads to detect the impact of drummer sticks. The automobile engine, which has, you see, a clear use of piezoelectric transducers to detect the detonation by sampling the vibration of the entire engine block, and also detect the precise moment of fuel injection, which has a clear needle lift sensors are there. And even we can say that the ultrasonic piezo sensors are used in detection of acoustic emission in the acoustic emission testing, where it is required for the IC engine part. And the crystal earpieces are sometimes used in, we can say, old or low power radios, where you see we just want to see that what exactly the impacts are there under the earpieces. So as you can see that the piezoelectric disc, which is straightway applied there, and you see here it can be act as, you can say, whatever the sensing features are being coming out as a sound, and that is immediately the pickup part is there under the guitar pickup. So this is, you see, one of the best part of the piezoelectric material is the sensing feature, the sensing application. But also you see here, as we know that this man-made piezoelectric part can be also used as the actuator. So as very high electric fields corresponding to only a tiny changes in the width of the crystal, and this width can be changed with the better, we can say, in the better than the micrometer precision, making piezo crystal most important tool for positioning object with the extreme accuracy, and thus we can use this as the actuators in that. So when we are talking about the ceramics, there are various layers are there in the ceramics, and using these layers thinner than the 100 microns, which allow, you see, reaching then the higher electrical fields, even more than, we can say, the voltage of 150 volt. The ceramics are used clearly for exciting the features right from the whatever the within the ceramics part, right from when these intermolecular features are there. So, these ceramics are used within the two kinds of actuators, we can say a direct piezo actuator, or we can say the amplified piezoelectric actuators. So, like in these two types different actions are being there, and we can use straightway as an actuator of this ceramics part. So, while we are talking about the direct actuators, the stroke is generally lower than the 100 microns and amplified to the piezo, we can say just going towards the amplified piezo actuators can reach to the millimeter stroke in the actuation part. Just like you see the loudspeakers, where the voltage is converted to the mechanical movement of piezoelectric polymer film. The piezoelectric motors, in which the piezoelectric element is being applied to a directional force to an axle which is causing to rotate. So, due to this extremely like small disturbances being involved at the microns level of this piezo motor, we can view this a high precision replacement for a stepper motor, because you see here like at the molecular level all these small disturbances are being occurred in the piezoelectric motors, and we can straightway use in at the like the micro level precise motion there. The piezoelectric element can be used in the laser mirror alignment, because we know that wherever you see like the laser mirrors are there for proper alignment, these piezoelectric element, because they have the ability to move a larger mass, the mirror mount you see here, over microscopic distances, and that can be exploited to electronically align some of the laser mirrors. And by precisely controlling the distance between the mirrors and the laser electronic can accurately maintain the optical condition inside the laser cavity to optimize the beam output. So, this is one of the specific we can say application of the piezoelectric element as a actuator to just like put a proper balance, or like just give a clear mirror balancing part in this part where the laser mirrors are being there to align the things. A related application can also be adopted in the acousto-optic modulator, in which you see a device that is scattered a light of the sound waves in the crystal can be generated by the piezoelectric element, and this is useful for fine tuning a laser frequencies. Even we can see in our atomic force microscopic or any scanning tunneling microscopes can straightway employ to convert the piezoelectricity to keep the sensing needle close to the probe for that. And even the inkjet printers, in which the piezoelectric crystals are just used to drive the ejection of the ink from inkjet print head towards the paper. Even in the mechanical devices, the diesel engine, the high performance common rail diesel engines are just using the piezoelectric fuel injectors, and they are straightway using, instead of these solenoid valve devices, they have a clear actuation features as per the requirement. These fuel injectors are being adopted, and they are absolutely based on this piezoelectric part. So, active control of vibration using these amplified actuators can be straightway used in these way. The X-ray shutters, and you can see that you see the metal disc with the piezoelectric disc attached is used as the buzzer part, as you can see on the screen. And even you see here the amplified piezoelectric actuator with the multi-layer ceramics is being there, and you see these ceramics can be like applied to many of the applications where it is being required. Another application part from this piezoelectric material, the smart material, is the frequency standard, because we know that the piezoelectric properties of the quartz or any material is useful to standardize the frequencies. And the quartz clocks which employ a tuning fork can be made from like the quartz as the combination of both direct and converse piezoelectricity to generate the regularly timed series of the electric pulse that can be used to mark according to the time of this quartz clocks. Or we can say even the crystal quartz, which is we can say like one of the elastic material, has precisely defined the natural frequency according to its shape and size, you see here, at which we know that the oscillation is being happened, and that can be even used to stabilize the frequency of periodic voltage when it is being applied to such kind of crystals. So, when we are talking about the frequency standard, we need to check it out that what exactly the properties of the piezoelectric part is really like just to be useful to standardize the frequency. So, the same principle is critical in all the radio transmitted. Whatever you see, the radio transmission features are there, and the receiver in computers, wherever you see, it creates the clock pulse. So, both of these usually use the frequency multiplier to reach the megahertz and gigahertz range of frequencies, which is to be like standardized according to the exciting part. And then we have the piezoelectric motors. These type of piezoelectric motors is just like showing that you see how the actuations are there, and wherever we require the actions from the motor, these piezoelectric based motors are just giving, like the travelling wave motor used for autofocus in reflexes cameras. There you see we cannot even adopt the actual motors, the piezoelectric featured motor are straightway used for autofocus part. Even the inchi-worm motors is being straightway used the piezoelectric motor for their linear actuation or the motoring actions. The rectangular 4-quadrant motors with high power density means if we are requiring, you see, even up to 2.5 watt per centimeter cube power requirement, and the speed which is ranging from 10 nanometer per second to 800 millimeter per second, these like the quadrant motors can be straightway used, these piezoelectric motors. And this stepping piezo motor, which is used for like the stick slip effect, is always being like based on these piezo motors. So, what I mean to say that the various types of motors which are being available and the applications, if we are just going for a higher speed ranging or like a high power density or for any kind of stepping part, or even for like the linear motions inside, you see the cameras or wherever like the requirement is there, there is clear application of these motors are. And all these motors just based on the same principle as our piezo features, which is being driven by the dual orthogonal vibration modes with the phase difference of 90 degree, and the contact between the two surfaces are simply vibrate in an elliptical path according to the Hertzian feature you see here, which can produce the frictional force between these surfaces. And we know that one surface is fixed causing the other to move, and in this piezoelectric feature, the piezoelectric motor is just like we can say excites the piezoelectric crystal, and then by a sine wave is generated at the resonant frequency of the motor. And using this resonantial feature, a much lower voltage can be used to produce a high vibration amplitude. So, that is one of the beauty of the system, because in that you see here we are using the orthogonal vibrational mode in the multi-degree of freedom system. So, when we are talking about the orthogonal feature in the vibration mode, we know that there is a clear phase differences are there at these two contact points of the vibrating surfaces, and because of that we can generate the elliptical path in between these two like we can say surfaces at the frictional forces. And because of that we can say that whenever the resonant frequencies are being there of the motor, even we have a lower voltage through which these entire thing, the dual orthogonal vibrational modes are being there, is really generating the high vibration amplitudes. So, you can see this is one of the beauty of this like the slip stick we can say actuator. This is what it is there, you see here we have the piezo feature here, and these like this sticky part is being there. So, when we have a slow excitations, this piezo is clearly creating, you see like the change in that, even whatever we can say a small voltages are there, and this rapid contraction, the slow extension rapid contraction is clearly featured the high vibration excitations even at the low voltage side. Or even you can see that this is what you see the actual motor part. It's a very, you see, like just the in a small micron size, and this stick slip motor is absolutely works on the using the inertia of the mass and the friction of the clamp. So that is why you can see that they are absolutely small, through which we can generate the high vibration amplitude. And some are used for camera sensor displacement, which are just like putting a anti-shake functions. So nowadays, whenever you see, like we are buying the camera, the anti-shake, like the functions is being there within the inbuilt part is absolutely coming through this stick slip motors, which is based on the piezoelectric materials. So we know that, you see, even with this particular small part, this SPA motor, we can clearly like put the anti-shake function in the cameras. So especially when we are talking about the piezoelectric application in the reduction of vibration and noise, the various researchers investigated the various ways to reduce the vibration in the material by attaching the piezo elements towards the material part. And when the material is bent by the vibration in one direction, the vibration reduction system respond to bend and send the electric power to the piezo element. And this technology can be, like expected, just that you see here, that whenever we are just sending these, like whatever the electric power part through this piezo element is to be like used to bend in other directions as well. So what does it means that you see here, whenever we are just trying to reduce or we just want to divert the whatever the propagation path towards the propagation path of these, like the waves, the sound waves or the vibration phenomena, this is one of the specific use, because we know that when the material is bent by this vibration in one direction, it can be respond to bend and even sends the electric power towards the piezo element to needs to be bent in other directions. So you see there is a clear variation there, and we are using this concept in cars and houses to reduce the noise part. So you see here, like in somewhere in 2005 in the Frankfurt, in the laboratory of this material vision part at the Darmstadt, the TU University, they shows various panels through which there is a clear hitting in the vibration part, means through the vibration part on the rubber mallet, and the panel with the piezo element is immediately stopping all these swinging feature there itself. So these piezoelectric ceramics fiber, which are just being used there, you see, like as an electronic damping system on some head tennis racket, we can see that there is an effective control on the swimming feature using this piezo element part. So when we are talking about, you see, the vibration control, the first thing is coming the measurement of that, and these the sensing part particular, and these sensing feature is straightway there based on the piezoelectric accelerometer. So this piezoelectric accelerometer is utilizes the piezoelectric effect of the certain material to measure the dynamic changes in their mechanical variables, like the acceleration or the vibration magnitude or the mechanical shocking. So as with all the transducer, the piezoelectric accelerometer convert one form of energy into another and provide an electric signal in response to the quantity, property or the condition that is being measured based on, you see, what kind of, like the dynamic actions are. So these piezoelectric accelerometers can straightway provide not only, you see, like the magnitude in one direction, but even bi or tri directions as well. Means in all three directions we can get the proportion of the acceleration at the same point. So using the general sensing method upon which all the accelerometers are based, the acceleration acts upon the seismic mass that is being restrained by a spring, or we can say suspended on the cantilever beam, and that converts the physical force into electrical signal. So before the acceleration can be converted into the electric quantity, it must first be converted into either the force or the displacement part. So that means you see here whatever the acceleration feature is there under the like we can say the movement of or the dynamic action of this mass, first it has to convert into the force or the displacement part, and this conversion is done by the mass spring system, as we can simply show there. So when it is being converted there, you see this is what it is. We have a piezoelectric accelerometer in which the crystal feature is there in this way. This is what my crystal feature, this is the added mass is there, and this is what my casing part. So when we are saying that we are trying to now measure the acceleration, so first this acceleration has to convert it into the electric quantity, and before that you see here first the force or displacement has to be coming out. So you see here when we have seen this mass, this is basically like putting this acceleration into, we can say, force as the inertia force, rather we can say, or the displacement part. And the piezoelectric these accelerometers, then you see just giving whatever the outcome is there in terms of the electric features, whatever the voltage changes. So these accelerometers are widely accepted as the best choice for measuring an absolute vibration in terms of the acceleration, because we know that the acceleration is not only depending on the amplitude, but also it is depending on the frequency features, how many number of times the repetitions are there. So the compared to other types of sensors, the piezoelectric accelerations have the great advantage, because we can apply for the wide range of dynamic range, means the for low frequency, higher frequency, low output noise, or whatever you see like the high output features are there, for the shock measurement, as well as for all type of you see the imperceptible vibrations. Excellent linearity like in measurement over the various huge dynamic range. The wide frequency range can be straightaway measured. It's especially you see compact, even you can find a small part for even like the higher frequency range with the high sensitivity. And we know that since all the robustness is there in that manufacturing part, so there is no moving part, so there is no wear and tear, and everything is self generating, so no external power source is required for that. And since the great variety of models are available, so you see here we can straightway use based on their linearity property. An acceleration signal can be integrated to provide the velocity or displacement. So that is why you see here the acceleration feature is one of the significant feature to measure the vibrations. The high impedance sensor output needs to be converted to the low impedance signal first, and for processing the sensor signal to a variety of the equipment that can be even used in the time domain equipment, where you see the root mean square or the peak amplitude meters are being there. The frequency analysis, straightway we can convert this acceleration, and then we can straightway analyze the frequency, the exciting frequency with the amplitude, and the recorders also can be used straightway. Even in the PC instrumentation, even for the capability of these equipment would be even wasted without an accurate sensing signal. And in many cases the accelerometer is the most critical link between the measurement chain, and to obtain the precise vibration signal, the vibration accelerometers are absolutely, even from the weight side, that you see like even the less weight accelerometer, the piezoelectric these accelerometers are there, or even you see here whenever we are going for higher operating range with the sophisticated sensitivity part, these piezoelectric accelerometers are well available in the market. So when we are talking about these accelerometers, the design of accelerometer is absolutely based on the various features, like it is based on the shearing system, whether the mode is shear or the mode is compression or the mode is bending or the flexural one. So the reason for using different piezoelectric system is the individual suitability for various measurement tasks and their varying sensitivity to the environmental influences. So we can say that there are you see like drawbacks or the advantage of such systems. So when we are using the three different systems like the shear or compression or bending or flexural, we can say the advantage is when we are using the shear feature, the shear system, we can say the low temperature transient sensitivity, and even it has the low base strain sensitivity together. But the disadvantage is it has a lower sensitivity to the mass ratio, whatever the like the added and the vibrating mass ratio is. And if you are using the compression system, the advantage is it is very sensitive to the mass ratio, which is a drawback of the shear system is. Even it has a good robustness in the design part, and it is a great technological advantage from this feature. But the main problem comes when we are using the compression feature, compression system in this piezoelectric accelerometer is the high temperature, we can say the transient sensitivity. So whenever we have, you see the transient nature due to the temperature variation, the inaccuracies are coming in the measurements. And when we are going towards the flexural or the bending system in this like the accelerometers, it is always best suited for the mass ratio sensitivity. But again, you see the various drawbacks are there in that, as it is very fragile in its nature. It is relatively high temperature transient temperature sensitivity. So you see here with this concept, certainly we would like to find out that what is the like the applications and where do we just want to apply that. So if you are going towards this design of this, you can see the first is the shear design, which is to be applied in major part of the modern accelerometer due to its better performance as per the compression and the bending part. And you see that we have like the shear forces, as you can see that the shear forces are there all along the plane, and due to the shearing action, whatever you see like the things are being coming can be straightway measured, as we have seen in our the basic concept. You can see the construction feature of that. This is what our covering part, the seismic masses are there, because you see we just want to first convert the acceleration into the force or the displacement. So this is what the seismic mass, and this is what you see the shearing feature of this piezo ceramics part is there. And then this is what the base where the excitation features are being coming, or any like these mechanical these accelerations are being featured out. So what I mean to say that when these forces are being acting here, it is absolutely in the shearing feature, and it has a great application because of the shearing force. There is a clear voltage generations are there in between that. And these shear mode design, either we can say the sandwich form or we can say like the bonding form, is just sensing the crystals between the center post and the seismic masses, as we shown by the dark region. And the compression ring or the we can say the stud in between, you see like the things are being there, applies the preload force which is required to create a linear region in the entire structure. And under the acceleration, this mass causes the shearing stresses which is being to be applied to the sensing crystals. So by isolating the sensing crystal from the base or the housing, the shear accelerometers excel in rejecting the thermal transient, whatever you see like the temperature transient features are there, and the base bending effects. And that is one of the unique feature in these shear mode, the shear base accelerometers, that you see here it is always being comfortable under the like a working feature of the thermal, or we can say the bending effect at the base part. We can apply these things. Also the shear geometry lends itself to a small size which minimizes the mass loading part or the inertial features on that, on the test structure. So that is why you see here we have a small like the sensor feature, the sensing devices are there which has all the features which is been required with the cancellation of the like the transient thermal and the bending part. And with this combination, the ideal characteristics, the shear mode accelerometers offer the optimum performance in the recent time. And if you are going to the compression part, you can see that it is a clear compression part is there on the piezoelectric material. So again, this output cover you see with the base, when like the excitation is coming and these bolts are being provided, under which you see we can say that the seismic mass is with this particular piezo ceramics part is there. So it is well like we can say balanced part, and you see because like it can contain the high compression features there itself. So compression mode accelerometers is simply offering a simple structure, we don't have to like go with the different combination of the seismic mass and entire like the feature. It has a good rigidity part, and we can say that it is simple base because you see like because of the simplicity part it is very much available. So, we can say that even there are three basic types of the compression designs are there, like upright, inverted and isolated part, and they are all available with this. So, upright compression, which designs you see like based on the sandwich part of the piezoelectric crystal between the seismic mass and rigid mounting base, is very much available in these markets, and they have a good, we can say, the compatibility as per the requirement. So, an elastic or the screw sensor means you see like when we are saying that the stud or the screw which is there in the like in this particular device is always secures the sensing element to the mounting base. So, when the like we can say the sensor is being accelerated, the seismic mass increases, or we can say whatever like the decrease or increase of this mass, amount of force acting upon the crystal and the proportional electrical output is being there. So, whatever you see the acceleration part which is being like coming to the system, the seismic mass is just converted into the force, and accordingly you see the electrical output is being there from this crystal part. So, the larger seismic mass, the greater stress, and obviously the greater outputs are there from this upright compression systems. And when we are going to the flexural feature, means the bending force, you can see that this is what like the piezoelectric part, the bending features are there, and you see these piezoelectric sensors which is being there you see here, and there is a frictional coupling is there along with this part, and we have the spring element. So, this seismic mass along with the this damping pistons are being added with these piezo ceramics, and you see here when at the base excitations are coming on that, the flexural mode part is being there according to their beam shaped sensing design with the crystal part, which is even then supported to create the strain on the crystal when the accelerations are there. So, in this the crystal may be bonded to a carrier beam, which is then increases the amount of strain under the high accelerations. So, this design certainly offers a low profile, lightweight, excellent thermal stability part, and you see here since like it is a simplicity in the design, they are quite inexpensive too. So, insensitivity to transverse motion is also one of the inherent feature of this design. So, generally we can say the flexural beam design are well suited for the low frequency, the low gravitational acceleration level applications, and that can be straightway like adopt along with the structure which is being tested at this low frequency part. So, when we are talking about the accelerometer selection, we need to go with the two main part, what is the criteria and what the accelerometer properties are being there along with that. So, when we are talking about the criteria, first the magnitude and the frequency, these are the two basic part of the vibration in this particular acceleration. So, we need to check it out, what is the sensitivity level in the accelerometer, what is the maximum acceleration responses is there from that, and what is the resonant frequency, the maximum resonant frequencies are there from that. The second criteria is the weight of the test object. So, if we have the maximum weight of these like the things are there, we can go the accelerometer weight 1/10 of the object weight. Then only we can say that there is a compatibility according to the inertia forces being generated, and then you see here at the base excitation it can be immediately sensed out towards that. The third, which is most important criteria, is the temperature transient, the strain, the magnetic field, or you see what the extreme acoustic conditions are there in the surrounding, and the humidity part, because they have a clear influence on that. So, excess influence, choose the sensor according to the characteristic that you see whether we are going with the shear, or whether we are going with the longitudinal, or whether we are going with the we can say like these bending features of that. And then we have the measurement of vibration velocity and the displacement. So, we need to check it out that whether you see the integration is a perfect part or not along with the shear accelerometer, and we need to check it out even sometimes below 20 hertz whether it is really preferable to use this one or not. Then the mounting, which is one of the important part in the accelerometer. the quick spot measurement below 1000 hertz, the temporary measurement and the long term measurement. When such kind of things are there, we need to see the property in the accelerometer, that whether we are using the probe, which is quick part, whether we are using the like the magnetic feature or the wax or any additive part, means the adhesive feature is there, so that we can permanently or temporary make an arrangement, or use the mounting stud or screws, or we can say we can simply prefer the sensor with the fixed cables. The other we can say criteria are grounding problems, means you see what exactly the grounding parts are there, which is simply using the insulating flange or the insulating sensors, or the long distance between the sensor and the instrument where the entire measurement is recording. So we need to see nowadays, which is perfect use, you see the accelerometer with inbuilt electronics, means the ICP kind of compatible part. Because when we are using the ICP type of these piezoelectric sensors, then you see here we can integrate the highly sensitive feature, and even that can be maintained up to the distance, the long distance between the measuring and the recording part. So in this part you see here the piezoelectric sensors and the actuators are various applications which we have discussed, especially when we are going towards the various those rotating machinery or any kind of vibrating generation feature. We know that the piezoelectric application in the material can be immediately acted as a sensor or actuator to suppress these vibrations, and you see here we can rather use even for many other applications of these piezoelectric featured in the materials. So this is, you see this chapter was mainly dedicated towards the applications of the piezoelectric materials. Now you see in the next lecture we are going to discuss about the application of these piezoelectric part, especially in terms of accelerometer and many other part under the active vibration control. Thank you.